So let's begin. So what we saw last time was that if you're interested in studying n-Selmer groups of elliptic curves for n equals 2, 3, 4, and 5, we'd constructed a semi-simple group Gn and a co-regular representation of it, Vn. And by co-regular, I just mean the ring of invariants is freely generated. In our cases, it's always generated by two elements. And we needed to understand GN Q equivalence classes on, well, not everything inside V and Z. We needed only the sort of locally soluble elements inside V and Z. We had defined a notion of local solubility, and we needed to understand how to count the number of G and Q equivalence classes on V and Z. So we're going to begin today by asking a slightly simpler question, namely, we're going to consider a semi-simple group G. You can also do this for reductive groups, but I mean, I'll stick to the slightly, it's pretty much the same, but let's say we have a semi-simple algebraic group G, and it's acting on some representation. And let's say we have a notion of a height. So we have a GR invariant function H from VR to R greater than or equal to 0. This is some kind of, we'll think of this as some kind of height. And we want to ask, the most general question we could possibly ask is, how many GZ orbits on VZ have height less than X? Now, it turns out this is not quite the right question to ask. What we have to do is we have to throw out some elements of VZ. We're going to have to throw out some elements of VZ because keeping them in sort of gives us a strange answer. As you'll see, there are two good reasons to throw them out. So I will refine this question in all the examples we consider. But for now, basically, we are going to look at what we'll call for now irreducible elements. So basically, there's a notion of reducibility. And so inside VZ, we're going to have some elements that we'll consider irreducible. And I'll sort of tell you what this notion of irreducibility is. As you see, it's a very important notion. It's crucial for framing a question as well as possible. So let's begin with one of the most classical example. Let's take G to be SL2, and let V be the space of binary quadratic forms. So elements in V are of the form ax squared plus bxy plus cy squared. And G acts on V by a linear change of variables, where gamma f of x comma y is just going to be f of x comma y dot gamma. So we have this this nice action. And what we want to do is we want to count the number of GZ orbits on VZ. So first of all, I will tell you two things before we even get started. First of all, I have to tell you what the notion of a height is. So in this case, it's very easy to define the height because remember, we need our height to be GR invariant. So it turns out that the ring of invariance is generated by a single element. And that element is the discriminant, where the discriminant, of course, is b squared minus 4ac. So the ring of polynomial invariance is generated by the discriminant, which means our natural height function is going to be the discriminant. The absolute value of the discriminant. So then our question is, how many SL2Z orbits are there which have bounded discriminant? But as you can see, this is not a very good question because the answer is always infinite because there are infinitely many SL2Z orbits which have discriminant 0. So at the very least, if we want a well-formed question, we're going to have to throw out the discriminant 0 elements. In fact, you should, the correct thing to do is to take the notion of irreducibility to be the usual notion of irreducibility. So an element f of x comma y in VQ is irreducible if it has no rational root. This is a very natural notion of irreducibility. And so now our question becomes, how many SL2Z orbits are there on irreducible binary quadratic forms with height less than x? And it turns out that this question, so I mean, this question was first studied by Gauss, who was trying to understand these class numbers. And so I'll just note that suppose you take VZ IRR with discriminant D, let's say D is not equal to 0, then this number, then the number of orbits this is going to be in canonical bijection with elements in the narrow class group of the field Q root D. So, sorry, and let's say D a fundamental discriminant. So D is square free away from 2, and at 2 it's at most divisible by 4. So this is a natural bijection with the narrow class group of the quadratic field Q square root D. And in his study of these class numbers, sorry, so this is not quite true because we've imposed this notion of irreducibility. So we're going to have to take elements in the narrow class group that are not the identity. Turns out the reducible elements correspond to the identity element, and so irreducible elements correspond to non-identity elements. So in his study of these class numbers, Gauss studied these orbits, and he had various conjectures for what this size should behave like. So it turns out that when you restrict to counting discriminant negative, you get a very clean answer. And let me make sure I get this correctly. So the theorem, so the first part is due to Mertens. And this was proved a very long time ago. And what he proved was that if you take elements in VZ with negative discriminant, up to x, so height is less than x, but the discriminant is forced to be negative. Take the irreducible elements and quotient out by SL2Z. Then this size grows like pi divided by 18 times x to the 3 by 2. Now, as you might expect, the positive discriminant case is significantly more difficult. And the reason it's significantly more difficult is because class numbers of real quadratic fields are difficult to study. You have to kind of, you can't quite, like you can't really separate the class number from the regulator. So you will end up, you can't actually count the number of orbits, but you can count the number of orbits if you weigh it by the regulator. So here, what I'm going to say is I'm going to sum over d less than x, but positive, and we're going to count the number of we're going to count the number of SL2Z orbits on VZ, irreducible elements in VZ with discriminant equal to d. But we're going to have to weigh this by log of the size of the fundamental unit. So this is going to be the fundamental unit. So in particular, it's the smallest, it's the size of the smallest Pell equation, the smallest solution to the Pell equation. So, but if you weigh it in this way, then you can actually compute the asymptotics, and you get pi squared divided by 18 times x to the 3 by 2. And this was the result of Siegel. Proved significantly later.
Sorry, just a question. This V is
the
specific example you said, right?
Very specific. So this is the example where we have SL2 acting on binary, acting on absolutely binary quadratic forms.
I wondered if the definition of irreducible needs to be tweaked a little bit, because as you've written it, reducible would simply mean that D is a square, but perhaps you want to also say that the form should not represent the number 1.
No, I don't want to say that. I want to throw out just the reducible, just the actually reducible ones. Oh, I see what you're saying. No, I don't want to say that. Sorry, you're absolutely right. You're absolutely right. This is not correct. It's just in bijection with the class group. So we're counting the whole class group here.
Mm-hmm.
Sorry, I confused this with the binary cubic case. You're absolutely right. I want to keep this notion of reducibility, but we will also be counting the identity element.
All right, thank you.
Thanks very much. Yeah, very, very good catch. Okay. So using a very similar method, Davenport studied what you could consider to be the next case, which is understanding orbits of binary cubic forms. So this time I'm going to state that, I mean, Davenport's result is, you're studying, I mean, the group is reductive, but that's fine. So I'll take G to be GL2Z and V to be the space of binary cubic forms. Same actions through linear change of variables. And this time there's no subtlety where you have to weigh forms by some regulator like factor. This factor shows up because the stabilizer in VR of an element is dimension 1. So in all our cases, the dimension of the stabilizer is going to be 0. And so we will never see a factor like this regulator showing up in this talk. So in the case of binary cubic forms, you can ask the same question, but now again, the same notion of reducibility. So f of x comma y. So we'll be looking at the set of reducible elements. Sorry, irreducible elements, where again, reducible just means you have a rational root. Once again, the ring of invariants is generated by a single element. Namely the discriminant of the binary cubic form. And so you can ask the same kind of question. How many GL2Z orbits are there on integral binary cubic forms having bounded discriminant? Once again, it makes sense to separate out the negative discriminants from the positive discriminant, and I'll state Davenport's theorem. So the number of GL2Z orbits on irreducible binary quadratic forms having discriminant, well, let's do the positive discriminant case first, this time. 0 less than d less than x. This grows like pi squared over 72 times x. While the number, the corresponding number with negative discriminant grows like pi squared over 24 times x. And Davenport and Siegel and Mertens all proved their results using geometry of numbers methods. And these are the methods that we are also going to explore. But I will first, excellent question. Is what true for binary forms of higher degree? So there's a question in chat, but I'm not exactly sure what the it is referring to. Okay, so I should mention before I continue on that there were other methods that were developed. So in particular, work of Sato and Shintani developed a zeta function method for counting these orbits, and Shintani Oh, the generation of the ring of invariants. No, as we'll see already in the binary quartic case, we no longer have the ring of invariance generated by just one element. It is generated by two elements. And as the degree of the binary forms gets higher and higher, the ring of invariants just gets extraordinarily complicated, and we really don't have a great understanding of what this ring is in general. So this thing with the ring of invariance generated by a single invariant is a very special thing for binary quadratics and binary cubics. In general, when the ring of invariance is generated by just one element, we say that the space is pre-homogeneous, and most representations are not pre-homogeneous. So anyway, I mean, the story has many tangents. I mean, like there were different methods that were developed, zeta function methods by Sato and Shintani. So you can look those up if you're interested. Very interesting and powerful methods. For example, they improve upon the error terms that DavenpOrt recovers in the binary cubic case. So there have been many applications of these methods. However, we're going to talk about geometry of numbers methods because there's sort of been a revolution in the field of using these methods to count group orbits on lattices. And this revolution is due to work of Manjul Bhargava. So let me describe how these methods work. But let's describe it in our context. So let me turn again to the space of binary quartic forms. So suppose, so now again, we're going to look at, again, G. So this time G is going to be PGL2, and V is going to be the space of binary quartic forms. And the action, we'll get an action we'll get a twisted action. So the way gamma dot f of x comma y is going to be 1 divided by the determinant of gamma, the whole squared, times f of x comma y dot gamma. And you can check that this action, which you first define on GL2, descends to an action on PGL2. So we have an action of PGL2 on the space of binary quartic forms. And now the invariant theory is more complicated. So this time the ring of invariance, as we've discussed, is generated by two elements. And these elements are I and okay, I'm using a different normalization. So let's call these two elements A and B. And A is a degree 2 polynomial it's a degree 2 homogeneous polynomial in the coefficients of the binary quartic, while B is a degree 3 polynomial. And so now we have to define a height. So you could, so why is normalization? It's not needed here. I mean, I see it. So the question is, why are we using a twisted action in the binary quartic case? And it's so that we get a representation of PGL2, which is the most natural group to use if you're interested in understanding Selmer elements. Because you saw yesterday the parameterization of Selmer elements was in terms of PGL2 orbits. But you could ask this for GL2 orbits, you could ask for SL2 orbits, and it's pretty much the same thing. You won't really get too much of a difference. Okay. So we have a degree 2 invariant polynomial and a degree 3 invariant polynomial. The discriminant of a binary quartic can be written in terms of these, and the way I've normalized it is 4a cubed minus 27b squared. Now, we would like to order binary quartic forms by discriminant, but it turns out that's an extremely difficult thing to do. We don't know how to count GL2Z, PGL2Z orbits on integral binary quartic forms when they're ordered by discriminant. That's still a big open question. However, what we'll do to make this question a little bit simpler is we'll order it by a height in which we bound both A and B. The reason it's difficult to order by discriminant is because if you're counting up to discriminant x, for all we know, a and b could get really huge, but the discriminant could still be small because 4a cubed minus 27b squared is 4. It's hard to rule that out. It's hard to rule out that possibility. And so what we're going to do here is we're going to order by height. And we'll define it to be the maximum of 4a cubed and 27b squared. So we're kind of mimicking the discriminant here, but we're insisting that both 4a cubed and 27b squared be small, which is of course much, when we say the height is small, both 4a cubed and 27b squared have to be small, which is of course a much stronger condition than, just be clear, a of f cubed and 27b of f the whole squared. It's a much stronger condition than just demanding that their difference be small. So now our question is, how many, let's again fix, so let's look at BZ. Let's look at irreducible elements. So this time I'm going to impose a slightly different condition on irreducibility. So irreducible means has no rational root. And the reason I'm throwing out only those binary quartic forms that have a rational root is that they correspond, the ones with a rational root correspond to the identity element in the Selman group. We saw this last time because if you have a binary quartic form, the corresponding twist of E2 that we got were the 4 roots, and that twist is trivial, exactly if one of the roots is rational. So having a rational root corresponds exactly to being the identity element in the corresponding Selman group. And we're going to insist that, that you don't have a rational root. So you're a non-identity element. So the question is, how many GZ orbits are there on these irreducible elements? We're going to insist the height is less than x. And let's fix the sign of the discriminant. Let's fix the sign of the discriminant. And let's call this number something. Let's call it n plus minus of x. Okay. I'm going to make one more condition. I'm going to insist also that the binary quartic that we have is solvable over R. So remember, yesterday we gave a criterion for when a binary quartic form is solvable over a field, and that's when it represents a square. So when the discriminant of f is less than 0, sorry, when the discriminant of f is greater than 0, when the discriminant of f is greater than 0, then either the binary quartic form has 4 real roots or it is definite. If it has 4 real roots, implies either that f has 4 real roots or it's definite. Now, if it has a real root, then it clearly represents a square because it represents 0. So if it has a real root, then it's solvable. But if it has no real roots, then it doesn't always have to be solvable, because then it's a square of a binary quadratic form. And if it's minus a square of a binary, so if it has 0 real roots, then it's either plus or minus the square of some binary quadratic form. And if it's negative a square of a binary quadratic, sorry.
It could be the product of 2 different quadratics.
Yeah, it could be. Absolutely. So if it's got 0 real roots, then it's a definite form. And if it's positive definite, then it's solvable because it represents a square, because it represents a positive number. And if it's negative definite, then it's not soluble. And if it's not soluble, we don't want to count it, because our goal is to count Selmer groups of elliptic curves. So I'm going to throw out the negative definite forms because they're not soluble over R, they're not going to contribute anyway. If delta of F is negative, then F has two real roots. And therefore it represents a square because it represents 0. So we're counting PGL2Z orbits on binary quartic forms. We're counting those that don't have a rational root with height less than x. We're separating the delta greater than 0 and the delta less than 0 case. And we're insisting that it is solvable over R, so which all that means is we're throwing out the negative definite forms. So that's our setup. Now, how do we count these orbits? So the point is, if you want to count orbits, what you do is you look at VR, you take the R soluble elements, you take the height less than x points, you take the delta condition, either positive or negative delta condition, and then you construct a fundamental domain for the action of GZ on VR. So this is called reduction theory. Following Gauss, who constructed the fundamental domain for the action of SL2Z on the upper half plane, like it's a similar kind of question. You're trying to construct a fundamental domain for the action of GZ on this on some vector space VR. So once you construct this fundamental domain, all you're asking for is the number of integer points inside it. Except you're insisting that they be irreducible. And if we can count this number, then we're done. That's our answer. So the first step is to construct this fundamental domain. Now here's how we're going to construct this fundamental domain. First, we will construct a fundamental set for not the action of GZ, because GZ is complicated. I mean, GZ is a complicated group. If you want to understand GZ orbits on VR, that's a little bit complicated, but it's much easier to understand the action of GR on VR. And it's much easier to understand this action because we know the ring of invariants very well. GR preserves invariance, so all you have to do is understand how GR acts in the set of binary quartic forms having fixed invariance. So to understand this, here's what we will do. Let's take VR, restrict to the soluble elements, which means we throw out the definite forms. We fix invariants A and B, which have discriminant not equal to 0. Now, GR actually acts on this set because G preserves the invariance. And let's ask ourselves what this quotient is. Now, if you'll remember, we have already seen from our parameterization theorems that this is in bijection with EABR mod 2 EABR. And this is a set which either has one element So this set has one element if the discriminant is negative, and two elements if the discriminant is positive. E of R is not mysterious. We know what elliptic curves over R look like. And I'll tell you what these elements are. I mean, if there's one element, it's pretty simple. But if there are two elements, there's going to be one element with 4 real roots, and there's going to be one positive definite form. That's all it is. So that tells us what we should expect this set to look like. And we're going to describe the set. So we're going to construct a set Rx, which is a fundamental set for the action of, it's basically something which represents VR soluble mod GR with height less than X and either discriminant greater than 0 or discriminant less than 0. So I'm going to make two things, Rx plus minus. And here are the properties it's going to have. First of all, Rx plus has two elements with invariants AB for all pairs A comma B with height less than X and discriminant greater than 0. So it's going to have two elements because that's what we want. And similarly, Rx minus will have one element with invariants AB for all pairs A comma B with height less than X and discriminant greater than 0. There's going to be some nice set to be parameterized well in terms of A and B. Moreover, and this is also not difficult to construct, so I won't actually go through the details, but the point is that every element in Rx, plus or minus, means the coefficients of X, the coefficients of F are going to be bounded by X to the 1 by 6. It's not too bad. The coefficients are bounded by X to the 1 by 6.
So for Rx minus, the discriminant should be less than 0.
Oh, yes. Thank you. Thank you. Absolutely. Okay. So once we have these sets Rx plus minus, what we're going to do is we're going to take F dot Rx plus minus, where F is a fundamental domain for the action of GZ on GR. And we're going to take F dot Rx plus minus, and that's going to give you some nice set inside VR plus minus. Okay. Now, we know what F looks like, especially in these cases. F is some nice fundamental domain. We can make it using Gauss's fundamental domain. And it turns out that this is going to be a cover for GZ on VR plus minus. We've thrown out the insoluble elements, only soluble elements are left. Height less than X. And when I say plus minus, I just mean discriminant either greater than 0 or less than 0. Now, it's a cover. Moreover, every element, or rather every GZ orbit of some binary quartic is going to be represented. We can say more than it's just a cover. We can say what the size of the cover is. So each orbit is going to be represented as often as the size of the stabilizer in R. So in GR, the size of the stabilizer in GR of F divided by the size of the stabilizer GZ. Now the Z stabilizer is not important because most forms are going to have trivial Z stabilizer. So we don't have to worry about the Z stabilizer, but the R stabilizer is interesting. That actually there's always a stabilizer, and we know what the stabilizer is. Because using a parameterization theorem, what we showed is that the stabilizer of F is isomorphic to the 2 torsion in the corresponding elliptic curve. So using the parameterization results, we know exactly what the size of the stabilizer is. So in particular, we have a cover and we understand the fibers very well. So our next goal then is to count the number of elements in this thing. The number of integer elements, but not all integer elements. We only want the irreducible integer elements. Now, unfortunately, this is not an easy thing to do. The reason is, even though Rx is a very nice set, we understand what Rx is very well. We have a nice bounds on the coefficients of everything inside Rx. But F is non-compact. In fact, I can describe F quite nicely. It's basically things of the form 1n1 times T inverse T times some element K, where K is contained inside SO2R. So K is not a problem. K is contained inside some compact group. T is going to be bigger than some constant. I've forgotten the constant. Something like this. I don't know. It's some non-zero constant. And N is going to sit between -½ and 1/2, unless T is small, in which case N is a little bit more complicated, but it doesn't really matter. N is always absolutely bounded. But the problem is that T can go to infinity.
I believe it's the 4th root of 3 divided by the square root of 2.
Thank you. The problem is that T is not bounded. So because T is not bounded, this is going to be some absolutely horrid non-compact set. And in the binary cubic case, you get something similar. You get some non-compact set, and Davenport went to all sorts of trouble in order to count the number of elements in number of integer elements in a set that looks like this. However, Manjul Bhargava invented an averaging method that takes this extraordinarily difficult problem of counting points, integer points inside some non-compact set, and simplifies it greatly. So what Bhargava's averaging method does is the following. So first you start off by taking a nice ball G0 inside GR. So let's take this to be open and let's take it to be bounded. Some nice round open ball. Its boundary as measure 0. All like you can take it to be anything. Take it to be the nicest ball you can think of. And then the idea is that if f Rx plus minus is a fundamental domain, then so is Fg Rx plus minus, because Fg is also a fundamental domain for the action of Gz on Gr. So adding a little g here should make a difference because it's a fundamental domain as well. So the number of points has to remain unchanged because they're both fundamental domains. So let's do an averaging. Let's integrate G in G0. And then using the fact that G is unimodular, you can deduce that this is going to be equal to, you can switch the integral from 1 over G0 to 1 over F. Translation by G? No, I don't think so. I don't think Minkowski used this, but it has been used before. I mean, like this kind of translation by G was used, for example, by Siegel when he studied lattice packing problems. It's also kind of used by the people who are developing Shintani zero function methods, but never as cleanly as this. This was a huge breakthrough, because now the point is that we are counting integer points inside a bounded set. We've gone from having to count integer points inside non-bounded sets to counting integer points inside bounded sets, because G0 is bounded, therefore G0 Rx plus minus is bounded, and translating it by any fixed element gamma is going to keep it bounded. We still pay a price. The price is that F is non-compact, and so as gamma goes up in the cusp of F, these balls can become very skewed. So when gamma is absolutely bounded, if gamma is some small element, then G0.Rx, you can just think of it as a nice round ball, and then counting points inside it is quite a simple matter. It's just approximated by the volume of the ball. But as gamma goes up in the cusp, you get some very skewed ball. And counting integer points here is not as easy because you can have a large error term. So basically but now that we have bounded balls, we can get started. The point is that the number of integer points inside some so this has to be nice. It satisfies few technical conditions, but all these definitely satisfy those conditions. The point is that this is always going to be usually well approximated with the volume, but there is an error term, and the error term is basically the surface area. Because as usual, if you have lots of points near the surface, you can't really tell whether they're in the ball or outside the ball, so you get an error term which looks like the surface area. So the issue is that as gamma goes up in the cusp, the surface area is getting larger and larger, and at some point it can even dominate the volume. So when gamma is below, when gamma is low in F, when gamma is essentially when T is small, when T is not growing, your volume looks like, I don't know, I mean, this your volume looks like, because all the coefficients here are bounded by x to the 1 by 6, the volume will look like the volume is going to look something like x to the 5 by 6, because each coefficient is around x to the 1 by 6, and there are 5 coefficients. So you get some volume that looks like x to the 5 by 6. And when gamma is small, the error is going to be around x to the 4 by 6. And that's great. Error term smaller than the main term, so you can compute the number of points very precisely. However, when gamma becomes large, so I'll tell you more precisely what the error is. So suppose gamma is some 1n1 times t inverse t times some compact thing. So something which sits inside a compact group, so times some k. The volume again is going to be unchanged because translation by gamma doesn't change the volume. The volume is going to be some constant times x to the 5 by 6. The error term, on the other hand, is going to be around t to the 4 times x to the 4 by 6. And the point is that as t gets large, and remember, a priori t is going all the way to infinity, the error term can absolutely dominate the volume. So, but then what happens is that as we go high up in the cusp, what you have to show are two things. First of all, sorry. So let me show this again. So we have t small, in which case the error is small, and we have t large, in which case the error is large. That's a problem. So what we have to prove is that when t is small, so we break up small t and large t into this. This is like when t is small, we say you're inside the main ball, and when t is large, we say you're inside the cusp. So it's a slightly artificial separation, but we basically break it up into a main ball contribution and a cuspidal contribution. And the main ball is when t is small and the error is small and you can count precisely. And the cusp is when t is large and the error is large and you can't count precisely. However, what happens is we show that in the main ball, most integral elements are irreducible. While in the cusp, all integral elements are reducible. So that's great, because where the error is large, we don't actually have to count at all, because every single integer point there is reducible, and we're not trying to count reducible elements. We're only trying to count irreducible elements. And all the irreducible elements are located inside the main ball, where we can count precisely. So that allows us to carry out the count in this case.
Sorry, can you repeat that again? I got lost a little bit. Yeah.
Absolutely. So our answer is in terms of an integral, and it's an integral over the fundamental domain. And the fundamental domain,
right,
there's this parameter t that shows up, and t can go all the way to infinity. It's bounded away from 0, but it can go all the way to infinity. Now the error term grows with t. So the error term is t to the 4 times x to the 4 by 6. And when t is large, the error term can dominate the main term. Right? Because at some point, t to the 4 is going to become greater than x to the 1 by 6. And then we're in trouble. However, what we do is we break up the integral into 2 parts. A part where t is small, I haven't precisely defined, it doesn't matter, it's pretty natural what the definitions are. So there's a part where t is small and there's a part where t is large. And when t is small, the error is small and we can count precisely. And when t is large, the error is large and we can't count precisely. However, what happens is that when t is small and you're in the main ball, most forms are irreducible. But when t is large and we don't know how to count, all the integral points are reducible. So we don't have to worry about large t at all.
I see.
So this error becoming large is just not a problem. Like we can prove that it just is not a problem because that only happens when the integral points are all reducible. Now, this is a pretty simple case because the group is just PGL2 and the cuspidal elements there, they're not very complicated. When n is equal to 5, we're counting 5 Selma elements. Sorry, I'll just take 2 more minutes and say this last point, and then but so I just want to say when n is 5, when you have 5 Selma elements, the fundamental domain of the group is extremely complicated because the group is something that sits inside. It's not quite, but it's something that looks like SL5 cross SL5. And the elements in the fundamental domain have a torus component, which looks like, there's an S1 to the minus 5, S2 to the minus 4, S3 to the minus 3, S2. I mean, it's to the minus 4, minus 3, minus 2, minus 1. Like these diagonal elements, the non-compactness, the torus is parameterized by 8 coefficients, like S1 to S4. Torus is parameterized by 8 coefficients, 4 of them for the first SL5 and 4 of them for the second SL5. And each of these can go to infinity and they can go at various different rates. And you have a 50-dimensional vector space. And you have to prove that every time the error becomes large, which can become large when any of these or some combination of these is large, that whenever that happens, it turns out that the same phenomena holds. In the main ball, most points are irreducible, and in the cusp, all points are reducible. And so what we do is we give a general recipe. So this is there in the 5 Selma paper. We sort of give a general method to verify that the cusp, and remember the cusp is just the part where the error term is large. Contains only reducible points. So we give a sort of general method to do it. And using the general method, now we can essentially, if G is a reductive group and V is a representation, we can count G, Z orbits on VZ. Like no matter how complicated G and V are, we've counted such orbits in infinite families. And so what this allows us to do is it allows us to compute the number of GZ orbits on VZ on irreducible elements in VZ in terms of a volume. Now it remains to compute the volume, but I'll get into that in the next lecture. And so I'll just stop now and take questions.
Are there any questions for the speaker?
Hi. Yeah. So let's say if you take some particular family of elliptic curves, then does the whole technique will go through? Like, will you get still some finer bound, or like let's
That's
say
a really great question. That's a really great question. And unfortunately, the answer depends heavily on what your particular family is.
Yeah, let's say
So,
like, for example, congruent number curves. I mean, like Heath Brown's has this bounds.
that's right. That's right. No, I'm afraid for such things it doesn't. Because right now we are counting all integer points inside V of Z. Like if you're looking at just the congruent number curves, you'll end up with a very sparse set inside V of Z. And counting the number of elements in that sparse set inside it is just a very difficult thing to do. So like one case in which you can count, this is work of Sam, Ruth, and Levon Alpoge, is if you look at elliptic curves of the form y squared equals x cubed plus b. So the a is 0. Now remember, this a corresponds to this polynomial invariant. You know, like when Vn acted on, when we had Gn acting on Vn, a was a polynomial invariant.
Yeah.
So now all we have to do is count the number of points inside a ball. So we'll have like some Rx plus minus, we'll have some G naught, and we'll want to understand the number of elements, but not inside all of Vz, but where a is also 0. So we're counting points not inside a lattice, but inside integer points in a variety. Now when n is 2, a has degree 2.
Yeah.
And you can use the circle method to count these points. And that's carried out by Ruth.
Okay.
And after that by Alpoge, who simplified the method greatly. And the idea is to use the circle method to count these points. Now, when n is 5,
so they bound the two Selma, right? I mean, you are saying n equal to 2.
you can compute they compute the exact size of the two Selma. But when n is 5, for example, the degree of a is 20. And then you're out of luck. The circle method is not going to do anything.
Okay.
There are other cases where we might be able to use some methods. For example, if instead you're looking at b equals 1 or b is something fixed, then there are ergodic methods that could be used, and we're working on that now. So, I mean, but the answer is in most, like the congruent number family is not even a variety, it's just some sparse set.
Yeah.
And it's in general just a very, very difficult question. I mean, I should say that there are much better, like if instead you're looking at the family of quadratic twists of a particular curve, Alex Smith has essentially solved this entire question.
Yeah.
But that doesn't use this parameterization at all. That uses the fact that all those Selma groups sit inside the same H1. That the H1 of E2 is the same group. It's the same infinite group. But now you're cutting out various different pieces of it by imposing the local solubility conditions. And he has some brilliant methods to control that. And so there are different methods that are available, but this particular geometry of numbers thing works when you're counting points inside a lattice and inside certain very special varieties. And that's it.
So do you like have any idea like to have some, let's say, general method which can be like, let's say, proving for general P, not only for up to 5?
So you mean like go past 5 Selma?
Yes, like for example, over function field, we have these results of Landesman and all this, like proving all the Poon-Rines thing.
Absolutely. So the thing is that, I mean, you're right. I mean, it's a similar kind of difficulty that shows up. If you want to parameterize
Yes.
n Selma for larger n, then you can't do it by using, at least we don't know how to do it using group orbits in a vector space. You've got to use group orbits in some kind of variety. And I'm afraid over number fields, we just don't have the tools to count integer points and varieties, except in very special situations. We just don't know how to do that. Over function fields, you have cohomological methods, and there's beautiful work of Landesman and Rains in which they do it. But over number fields, you've got to make a nice variety. There are certain approaches, which is they're very. I mean, like I don't know of anything that's concrete and that's anywhere close to succeeding yet.
Thanks.
Not at all. Thank you. So separate families. So that's a good question as well. Studying separate families and combining them. Yeah, I'm not sure. It's an interesting idea, but I'm not sure.
Any further question? If not, let's thank the speaker again. Thank you.
Thanks very much.